Back in 2010, the world got a pretty massive wake-up call. We all learned a shocking new truth that simple computer code, just lines of text on a screen, could actually reach out and physically destroy hardened steel in the real world. I mean, this wasn't science fiction. This was Stuxnet, and it completely changed how we think about cyber warfare. So today we're diving into the story of its incredible digital arsenal. So what's that number? Well, that's roughly how many high-tech uranium enrichment centrifuges were physically torn apart by a sophisticated computer worm. We're not talking about a bomb, not a missile, just a piece of malware. It's estimated this set back Iran's nuclear program by a couple of years, all without a single shot ever being fired. So this is the big question, right? This is the central mystery we're going to unpack. The target facility, a place called Natanz, was air-gapped. That means it was physically disconnected from the internet. It was supposed to be this impenetrable digital fortress. So how on earth did the attackers bridge that gap and turn a piece of software into a physical weapon? The answer? Well, it lies in a whole arsenal of secret digital exploits.
All right, so here's how we're going to break this down. We'll start with what Stuxnet actually was, and then we'll get into its most powerful components, these things called 0 days. After that, we'll follow its exact digital kill chain step by step. And finally, we'll look at the devastating payload and, maybe most importantly, what critical lessons this attack still teaches all of us today.
Okay, so first things first, what even was Stuxnet? Because this wasn't just another computer virus, it was something totally new. Think about it. Most malware wants your credit card numbers or your company's data. Stuxnet? It was built for one surgical purpose, and one purpose only: physical destruction. This was a nation-state level operation, something that took immense resources to create, and it's widely considered the world's first true cyber-physical weapon. Its code was like a digital scalpel, designed to find a very specific target inside a very specific facility and cause very specific damage. And here's what's so wild about this whole thing. An air gap is supposed to be the ultimate security control. You literally have a gap of air between your sensitive network and the outside world. No internet connection, no external network access. In theory, nothing gets in. Stuxnet proved that theory was dead wrong. So how do you break through a defense like that? Well, Stuxnet's creators used an incredibly powerful set of tools. And that brings us to the core of its arsenal, the 0 day. To really get what a 0 day is, let's use an analogy. Imagine a company sells millions of locks, but secretly there's a hidden design flaw, a flaw that lets a special kind of key open any of them. A 0 day vulnerability is that secret flaw. A 0 day exploit is that secret key. And the reason it's called a 0 day is because the software company has had 0 days to create a fix, because they don't even know the problem exists. For an attacker, this is the ultimate master key. Now, Stuxnet didn't just have one of these master keys, it had a whole ring of them. And it used them in a multi-stage attack process that we call a kill chain. So the worm's journey followed this really clear logical path. First up, it had to get across that air gap. Second, once inside, it needed to move silently through the network to find what it was looking for. Third, it had to gain the highest level of permissions, basically becoming the boss of any machine it landed on. And finally, it could deliver its destructive payload to the industrial control systems. Okay, so how did it actually jump that air gap? Stuxnet's first 0 day was pure genius. It was a flaw in how Windows handled shortcut icons. An attacker just had to get an infected USB stick into the facility. The moment someone plugged it in, their computer would just try to display the icons for the files on the drive, and boom, malicious code running. No clicks needed, you don't have to open anything, just viewing the icon was enough to infect the machine. And just like that, the air gap was breached. Once it was inside, Stuxnet had to go hunting for its real target. To do that, it used a second 0 day in the Windows Print Spooler, which let it spread to other computers through shared printers. It also used a well-known older bug called MS08-067. Now, the attackers were smart. They knew that in these kinds of high-security places, patching isn't always top of the list. So they used a mix of brand-new secret 0 days and old, reliable bugs, giving the worm multiple ways to spread. It made success much more likely. Okay, so Stuxnet is now inside the network and it's spreading like wildfire. But remember, its goal isn't just to hang out on some Windows machines. It's looking for a bridge to the physical world. Now, this is a really crucial point. Stuxnet wasn't a one-trick pony. It carried 4 different 0 day exploits just for getting in and taking control. Why? Redundancy.
It made the whole thing incredibly resilient. If defenders found one of its secret keys and changed the lock, no problem. Stuxnet would just pull out another key and keep going. After spreading through the network, Stuxnet was hunting for something very specific, a piece of software called Siemens Step 7. This software is used to program PLCs, or programmable logic controllers. You can think of a PLC as a tiny, tough little industrial computer that's in charge of real-world machinery, like the motors spinning those centrifuges. Finding an engineer's computer with this software was the key to crossing from the digital IT world into the physical, operational technology world. And the attack on those controllers, this was just a masterclass in deception. First, when an engineer connected their workstation to a PLC, Stuxnet would secretly inject its malicious code. But the genius part is what happens next. The worm would intercept all the normal data coming from the centrifuge, recording what a healthy machine looked like. Then it played that normal recording back to the control room operators on a loop, like a movie. So they're sitting there looking at their screens, and everything looks perfectly fine, completely unaware that Stuxnet was about to cause chaos. And this is what that chaos looked like. The malicious code would command the centrifuge motors to spin way too fast, from their normal speed of around 1,064 hertz up to over 1,400. This caused huge physical stress. Then it would go quiet for almost a month to avoid suspicion. After that, it would drop the speed way, way down, causing more vibrations and stress. This wasn't a quick smash and grab. This was a slow, methodical, patient attack repeated over months that was designed to physically tear the centrifuges apart and make it look like a simple mechanical failure. Eventually, the world did figure out what was going on, but Stuxnet's legacy, well, it permanently changed the game for anyone trying to protect our most critical infrastructure. And this right here is probably the single biggest lesson from Stuxnet. An air gap isn't some magical force field. It's just one layer of defense. And as Stuxnet proved, any single layer can be bypassed. Real security has to be defense in depth, with multiple controls all working under the assumption that any one of them might fail. So what are the big takeaways here? First, you can't rely on an air gap alone. They are not infallible. Second, old, unpatched vulnerabilities can be just as deadly as a secret zero-day. And that means the networks that control our power plants and factories need specialized security, not just standard IT stuff. And this changes our entire mindset. Now, when a machine breaks down for no reason, you have to at least consider that a cyber attack could be the real cause. For anyone out there who's actually defending these systems today, the lessons from Stuxnet give us a really clear playbook. First, given how Stuxnet got in, you have to enforce strict USB device controls. To stop something from spreading, you have to segment your networks to contain intruders. You need a plan to patch your operational technology. And so, critically, you have to monitor that OT network for weird behavior, because Stuxnet hid by looking normal. You have to know what your systems are supposed to be doing so you can spot when they're not. Stuxnet really did open Pandora's box. It was the moment that proved the digital and physical worlds are no longer separate. It showed that our most vital systems, our power, our water, our manufacturing, are vulnerable in ways we never really imagined. The question it leaves us with isn't if an attack like this will happen again, but whether we've learned its lessons well enough to be ready when it does.